Hello dear friends, welcome back to my channel. I'm Gerard and I'm here to study matrices together with you. And last time, the two previous times, we have seen the very basic of matrices. We talk about augmented matrices, reduced row echelon, form matrices, and reduce echelon form matrices. We talk about the quotient elimination method, and we talk also about the Gauss-Jordan elimination method, and what is back substitution, and so on, to avoid to go till the all the way to the reduced row echelon form. And we also talk about the theorem, which is the homogeneous system of linear equation. So if equations are homogeneous, or if system of linear equations is homogeneous, it means that the equations are equal to zero. And if they are equal to zero, it means that they are consistent. They have solutions. They have solutions. They have solutions. And we have two types of solutions. We have trivial, which means that the solutions are zero, or the solution, not the solutions, but the solution is zero. Or you have non-trivial. It can be infinitely many solutions. For example, two lines being the same, actually, or not exactly the same, but for a certain range, for given boundaries, they are the same. All right, so as promised, today we will start with something else. We're still dealing with lines, linear algebra. So we are going to start with the arithmetics. Arithmetic operations. What are the arithmetic operations? Of course, the plus, minus, so addition, subtraction, division, multiplication, and so on. So all these are arithmetic operations. So we're going to use matrices, which are arrays of numbers. So we should be able to do addition, subtraction, and multiplication. So we don't really do division and so on. So a matrix is a rectangular array of numbers. We know that the numbers are called entries. So we have one entry, two entry, three, four entries. And so we have number of rows. So we have first row, second row, first column, second column. Yeah. And for this one, this is a quadratic matrix. So it's two rows, two columns. So we write it like this. So, right, a matrix with one column is called a column matrix or column vector. So it looks like just like this. It means that you have 1, 1, for example. This is a column matrix or column vector. Matrices are denoted with capital letters. So this would be, for example, A. Matrix A, and this would be matrix B. Capital letters. Okay, denoted, the denotation with capital letters, and the entries will be like A, B, D, O. So these are small letters, and or in with lowercase letters. So I just give some examples, and numerical quantities are referred to as scalars. So we've heard something like vector, a vector, a column vector, more precisely, column vector. I'm sorry if I'm making a big mess, but this is the one, column vector. We know that vector has a magnitude and also or a quantum, if we can say it like this, quantum and direction. The vector has both, but the scalar has only a quantum or a magnitude. So numerical quantities are referred to as scalars. So this is what I understand. The entries are normally not vector, but they are just scalars. Scalars just have a number, a quantum. Okay, so let's have a look at some example, and then we'll try to. So A is 1A. These are entries. This is the denote of a matrix, and so this is a column. Is it the column vector? Yeah, or vector column? Yeah, column vector. Yep, and voila. Sometimes they don't use capital letter, they use bold, but bold is not possible here. So, and when we know there is a column vector matrix, and when it's like 2 times 2, this is called a square matrix. It can be also like 4 by 4, so the number of rows and the number of columns are the same. And let's say like this one, we have 2, 5, 4, and 10, and this is very important. This is called the main diagonal. This is called the main diagonal. I mentioned it before. Diagonal. This is the main diagonal. In matrices, this is like a key thing here. It's a key thing. We use the values in the main diagonal to solve things or to do things and so on. So the main diagonal of, if that's A, bold letter or capital letter, so the main diagonal is 210. Or I think you put the comma here, something like this. Okay, and so these are things that you have to know before even starting with the operations, arithmetic operations. But we're going to start pretty soon with them. So two matrices are equal if they are of the same size and the corresponding entries are equal. So what is equal? You know, in math you have different terms like equivalence. They are equivalent or they are equal, like A divided by B is equal to 1, so they are equivalent, something like that. I learned this. Please do not take me for granted, check it yourself. But you have like equal and equivalent. Equivalent means that they are the same. I think you put like three bars like this, equivalent. So if you have 1, 2, and you have 1, 2, this is a 2, 1 matrix. This is a 2, 1 matrix, but this is A and this is B. So A is what is is equal. They say are equal if they are not equivalent, but they are equal. And their entries are just the same. So that's why they're equal. What else? Two matrices can be added or subtracted only to each other, only if they are of the same size. So if they are not of the same size, you cannot do addition and subtraction. So very important. Addition subtraction. So the matrices should be of the same size. For example, if we have A here, we have 1, 2, we have B here, we have 2, 1, and we want to add them. So normally the result of A plus B is going to be 1 plus 2, 3, 2 plus 1, 3. But if we had something like B is equal to, let's say, just 1, just as it has only one entry, it does not have a column, it just have one entry, it's one column, one row. So how will we do the addition? Do we say that there is a 0 here? They say no. They say that we cannot do this. So we cannot do this. Subtraction is just the inverse of addition, so we don't need to do it here. So scalar multiplication. Scalar multiplication. Scalar multiplication. So what is this? We talk about vector column here like this, but what is we say that the entries are scalars. So scalar multiplication, we have A, we have 2, 3, this is a square, a matrix, and C is equal to where C is a vector. Okay, so C is equal to 2, and they say that C is a vector. So CA is equal to 2A. Then is equal to 2. 2 times 2, 4. 2 times 1, 2. 2 times 3, 6. 2 times 5, 10. So we have this CA is equal to 2A because the value is this, and it's equal to this. So this is scalar coefficient of A, the scalar coefficient of A. So that's why sometimes you can multiply by any coefficient to get rid of certain things and so on and so on. And it's just scalar multiplication, and you just multiply all the entries by the scalar you want. But we are not multiplying two matrices. So now multiplication of matrices. We're getting slowly there. Believe me, once you know it, you know it. So if you have A times B, so we know that for addition and subtraction, they have to be of the same size. Otherwise, you cannot do it. But remember the size, you always have the rows. So if you have 1, 2, 3, 4 here, here you have 2 rows, so you say 2. Have 2 columns, you say 2. So 2 times 2, it's a square. Okay, so we call this M, we call this R. Okay, so this is M times R, this is M times R. All matrices, they have the M and R. They have the number of rows, they have the number of columns. If you want to multiply, looks like something is different when it comes to multiplication, because they are not commutative. Commutative, yes. You know, associative and commutative. Commutativity. If it exists, if this word exists, check in the dictionary. So it means that B times A is not equal to A times B. So it does not have this commutativity. you cannot commutate, you cannot change the places. So you have to go in a specific order, the given order. So that's why it's like this. That's why it's like this. You have to you have to you have to follow the order. Follow the leader. 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 Okay. Here we're just using letters to refer to, because this one is 2 2. It could be MM, for example, and like this is like M times R. Let's say I'm just creating my own things, but this is not going to work. I will tell you something. Yeah. So for two matrices to multiply, you need to have this and this the same. So here the column is the same size as the row. Column, row. They should be the same. If they are not the same, they are not going to be, it's not possible to multiply them. That's a rule. Very important. So look at the size of the matrices, and you can say if they can be added, subtracted, and multiplied. Okay, guys, matrices can be multiplied if they are defined. The column size of A is equal to the row size of B. The result matrix is the row size of A and the column size of B. I'll give you an example. We have A is equal to 2, 3. Sorry for my 2, but yeah, it's very late in the night. It's 1:52 in the night, or in the morning, depending if you are a morning person or a night person. So, alright, so we have two matrices here. This one is 2, 1. This one is 1, 2. Can we multiply them? Yes, because the column number and the row, they are the same. So you have a smile. So if you multiply them, you will get now a matrix, a quadratic, a square matrix. And it's going to be 2, 2. 2 rows, 2 columns. 2 rows, 2 columns. Okay, so now we're going to learn how to multiply. How to multiply the two matrices. There is a very nice, there is a very older way, a specific way to multiply. So you have to take 2, the row, you multiply by the column there. So 2 times 1, you get 2. 2 times 2, you get 4. So 2, 4. Now you take 3 times 1, you get 3. 3 times 2, you get 6. 3 is 6. And that's AB. That's AB. That's the result of the multiplication. Alright, so we are done here. We're done because we did an addition, and the subtraction we didn't because it's just the inverse of addition. But multiplication, here it's done. So multiplication and so on. Now let's just do another example. We have 1, 2, 4, 2, 6, 0, and we have 4, 1, 0, minus 1, 2, 7. Notice that this one has only has actually three rows. 2 rows, 3 rows, 3 columns, 2 columns. So it's a 2, 3 here, and it's a 3, 2 here. Can we multiply them? Yes, because these are the same. What kind of thing we will get? We'll get a 2, 2, 2 by 2. So how do we multiply this? very important. We take this, we multiply by this. So we're going to go like this. 1 times 4 plus 2 times 0, sorry, plus 4 times 2. So what we did, we took this times this, this times this, this times this, and we're adding them, yeah? So what do we get? 4 plus 0 plus 8, 12. So we have 12. Now we do the same. First row, multiply by second column. 1 times 1 plus 2 times minus 1 plus 4 times 7. What do we get? 1 plus minus 2 minus 1 plus 28. Minus 1 plus 28, 27. 27. Okay, so this is done. Let's take this one. 2 times 4 plus 6 times 0 plus 0 times 2 is equal to 8 plus 0 plus 0, 8. 8. Let's take the second now. 2 times 1 plus 6 times minus 1 plus 0 times 7 is equal 2 times 1, 2. 6 plus 6 times minus 1. Minus 6, it's minus 4 then, plus 0. Minus 4. Here you go. This is A, this is B, therefore this is AB, because it's the multiplication. Very important, rows times columns. Not column times rows, rows times column. You will know because you always write the row and then the next row. You don't write columns. Well, anyway, you have whatever way you want to understand it, in whichever way you want to understand it, you need to do it properly. But there is also another thing that might confuse some people, but what I did is just the product of AB as linear combinations. So we did that one. Yeah. But there is another method for multiplication, still for multiplication. To be fair, sometimes it's easier, sometimes not. If you're familiar with it, you can use it. Or for me, I got confused the last time I tried to use it, because I'm only learning this module now, the linear combination. What I want to say is that, let's break this. Let's put like 1, 2, 2, 6. Normally it's not that small. I'm making it small. 4, 1, 0, minus 1. I don't know if it's even valuable. See if it's even correct to write something like this. We can multiply them because they're like this. So if we want the product, so we usually do like this. We multiply like 1 times 4 plus 2 times 0. We get a value, and then we're going to have a 2 by 2 because of this and this. Yeah, this is a result. So we're going to have like 1 by 4, 4 plus 0, 4. And then we do like 1 times 1 plus 2 times minus 1, 1 plus minus 2 minus 1. And then we do the second row. So we have 2 times 4 plus 6 times 0 equal to 8. 8. Then we have like 2 times 1, 2 plus 6 times minus 1 minus 6. So we have minus 4. We have something like this. And I don't know if it's correct, but yes, I think it's correct. Yeah, I followed all the rules, so it should be correct. But this is what we've learned before to do. But linear combination, they do something crazy. If you want to get crazy, you can try this. So what they do, they take like 4 times 1, 2 plus 0 times 1, 2 and is equal to, you know, yeah. So what do you get here? You get 4, 8, 4, 8 plus 0, 0. So you get 4, 8. So you get this. Incredible, right? It's faster, but you know what? You have to know what you're doing. So then you get 1 times 2, 6 plus minus 1 times 2, 6. As long as you know what you're doing, it's good. But for me, I got confused by what I did the last time, so I'm just warning you guys. So you get something like this: 2, 6 plus minus 1 times 2 minus 1 times 2. So, goodness, what am I doing? You see, I got lost. I got lost. That was the first result, yes. 4 times 1, 4. 4, 8. That was 4, 8. Yeah, 4, 8. Yes. Then you will get this 4. So you will get 4, 8, and then you will get like 2, 6. So 2, 6 minus what? Minus 2, 6 minus minus 2, 2, 6. Minus 2, 6, yeah. It's going to be 0 then. 0, 0. Looks interesting. Yeah, it's probably 0, 0. Yeah, but this is called linear combination. Not really good at it. But okay, we have spent enough time here, and the colons. Okay, and now we're going to look into some other things. Matrices can be partitioned so that we can calculate, compute only the entries of interest. So matrices partition. So they say that, for example, if you have this linear combination or system of equation, I'm writing too big, so I'm going to go back, erase 1, 2, 3, 2, 1, and I think we have 2 minus 3 minus 2. So we have this, and we have 2 minus 1 and 3, and then we have 1 minus 9 minus 3. So I computed this very quickly. So what we did is, this is a 3 times 3, very important, 3 times 3, and this is a 3 times 1. We can multiply, yes, we have a smile. And what we will have, 3, 1, 3, 1, 3, 1. Very important, very important. I'm going to erase what we don't have, and I'm going to write it in a clearer way, in a more beautiful way, because we're going to analyze what we're doing here. Sorry, I need to become more presentable, I guess, because when you do mathematics you have to be presentable. I think so, at least now I'm learning some of the things that a mathematician needs to know and needs to do. So what we do, usually we take this, we multiply by this. Yes, that's what we do. This is a 3 times 3, and then we have a 3 times 1. We get a 3 times 1. Yeah? You agree? I think you agree. So here we just do like minus 1 times 2 plus minus times 2 plus 3 times minus 1, yeah, plus 2 times 3. We have minus 2 plus minus 3 plus 6. What do we get? We get minus 5 plus 6, 1. We put 1 here. We take this, we multiply again. We get minus 9. We take this, we multiply by this. We get minus 3. We get this. And that's what is here. Alright, so what's new here? What's new here is that we can rewrite this. Remember, we had this linear combination and so on. What we do is just like bam. sorry. This is minus 1, 3, 2, 1. Bam. 3, and then 2 minus 3 minus 2. Bam. Is equal to. If you compute this, and you compute this, you add everything. So minus 2, 2 minus 2 times minus 1, minus 2, minus 1 times 3, minus 3. So minus 2 plus minus 3, minus 5. Minus 5 plus 3 times 2, 6. 6 plus minus 5, 1. So I did like only the top part here. Yeah. So I will get eventually the same result as this. So what we do, we just like write the column in a row here, and we put the columns right here in between. This is the combination, and it should be easier than the other one normally. But once again, for me, I was like, I had doubts of the I finished. So it's not good when a mathematician has doubts, because mathematicians should be confident. So well, I'm joking, but there is a part of truth here. So coefficient matrix, we saw that, like, we have a1 to 1, a1 2, a2 2. This is a simple, like, square matrix, this, and so we can have like a result like b1, b2, b, I don't know, there is no other b because I didn't want to write more than this. So what happens is that these are just coefficients. Like I said, we can have x1 here, x1 here, x2 here, x2 here. We can write these things here, but we're just reading the coefficients. Okay, so now we are going to learn something like ax is equal to b. What does that mean? There is a, there is x, there is b. What is b? What is a? What is x? I'm thinking that a is a matrix because it's a capital. And b is, this is an entry. X is an entry of this matrix, and b is something. B is here. B is probably the result. It's probably the result. Yeah. So there is something that you should know when it comes to coefficient matrix and so on. We were still with this. So A, I think I understand what it means. So, not pretending that I know everything. Sorry, I'm still learning. So if you don't believe me, you can go and check by yourself. I'm just doing my homework right now. Yes, really, I'm just doing my homework right now, and I can be making a lot of mistakes. It's up to you to believe me or not. So it's at your own risk. Do you want to take the risk? I don't know. It's late in the night. It's up to you. So what we did here, uh, here we have the coefficient here, the coefficients, yes, and we have the variance here, yes, the unknowns, and then we have b1, b2. So if we want to write an augmented matrix, we will have a11, a21, a12, a22, and then b1, b2. That's how we write it, because we have an equation and then e is equal to something. So if you want to write it in a way, you can write it like a bar b, a bar b, so a Barbie doll. So then you will have a here and b here. So the above is a coefficient matrix. So that's what they say. This is a coefficient matrix. You have the coefficients here, and you put the figure here. Here there is no x1, x2, or xn or something. So we don't have this. So this is how you write a coefficient matrix. So coefficient matrix. That was the title of this notion. Okay, so if someone says, do me a favor, write this on 1 2, again 2 1 a 2 2, and then we have x1. These are the unknowns. Actually, I didn't write more than this, so, and then I'm simplifying when I'm writing here, so I'm not writing all of them, but just like the two first, just for you to understand. If you make this multiply like this, you should 2 times 2 and 2 times 1. So all the compatible, can you multiply? Yes, smile. You will get it 2 by 1. This is a vector colon 2 by 1. So very possible to do it. And what's the time? 41. Okay, I think I can finish with this. So if you multiply, let's multiply, but we will try the difficult method. So difficult method is just something from here. You have x1. What was it? I'll try the difficult way. I don't care right now. Times a theta x plus. Oh, I cannot write that big because then there will be no space. So x1 times a11 a21 plus x2 times a11, yeah, a21, I don't know, plus, no, there is no plus because I didn't write all of them. So what we do here, we will have a on 1 x1, and then we will have a21 x1, right? Right. Yes. Plus, first time that I'm doing this, yeah. I don't know. I'm doubting that I'm doing the right thing here. A to 1x. I think here it's like, yeah, I made a mistake. Definitely, I made a mistake. I made a mistake. I made a mistake. It should be, that's why I'm not used to this. It should be like this. A12, A22. And then you get like the result here, A11, X1, A21, X1, yes? And here you will get, so you put it here, A11, X1, A21, X1, and then here you get A12, X2, A22, X2, and then you put it here, A12, X2, A22, X2. So you have done the multiplication, so ax here, and you see this is done. And what you can do now, if you, this is now just the coefficients and the unknown. If you want to include the the results here, you just put it here. You don't multiply. Alright, that was coefficient matrix. And as you can see, I'm not very good at doing this thing, but I need to learn how to. So slowly but surely we're moving forward, and we're already now going to talk about something very important, which is transpose of a matrix. What is a transpose of a matrix? The transpose of a matrix is just a transformation of a matrix. There is no other definition that I found, and so this is the matrix. It's a 3 by 2. We're going to transform it. We're going to make a transpose. So what we do when we do a transpose, we had this format. Yes, we're going to have like 2 3. So what does that mean? It means that we're going to take a column, we're going to make it a row. We're going to take a column, we're going to make it a row. We have transposed it. So it's kind of transforming, like maybe a line is like this, and you want like to transform it like that, you know, to make a reflection of it in this, or if you want to make a reflection of this in this. Actually, it depends what you want to do. Yeah, but this is transposition, as simple as that. Transpose of a matrix is a result from interchanging the rows and the columns of a matrix. So it is denoted like this with the T on top, and as you can see, so here it's like, how do you call this, the size, I think they call it the size, and is inverted. So the column becomes a row, the row becomes a column. This is transpose of a matrix. Okay, now we have another thing which is very important. It's the trace of a matrix. A matrix. So what is this? The trace of a square matrix is a sum. I think you can do it only for square matrix. Square matrix is like 2 times 2, 3 times 3, 4 times 4. You got the idea. So these are square matrix. You have other matrices. We talk about different names, but this is not a square. Now it is square, and this is a zero matrix. And you have also the, we call it like one matrix. The identity matrix, I think that's how you call it. The identity matrix, something like that. We call this. And the trace matrix, the trace of a square matrix is a sum of the entries and the diagonal, on the diagonal, sorry, of the matrix. Remember, I said there is, let's say there is this A11, A12, A13, A21, A what? A22, A23. Let's say there is another one, A31, A32, A33. So we have this big matrix, and it's a 3 by 3. This is the size. The main diagonal is here, and the trace of A is A11, sorry, is A11 plus A22 plus A33, and that's it. This is the trace. I don't know what it means really, how it can help you, in which way it can help you, but that's what you need to know. And properties. So now you're just learning how to manipulate the data from properties of transpose, sorry. So now you're just learning how to do arithmetic, like when you're learning how to do addition and subtraction, you don't ask why are you adding now, why are you subtracting now. It's just for the sake of knowing how to do them. But then you will have, oh, let me, yeah, then you will have some more explanation. So guys, what else? What else? So here are the properties. So properties means that these are things that you might need to know when you're dealing with such things. If you transpose a transposed matrix, you get the original matrix. Another thing is that if you have an addition of matrices transposed, it's the same as transposing each matrix and then adding them up. So when we talk about addition, it's the same also. It's also true for subtraction. So I'll just like, so this is second property. And there is also this property which is like, remember the coefficient matrix. So if you have a coefficient matrix and you just have the transpose, you can do it before multiplying, after multiplying, where k is a scalar. K is a scalar, so it's not a matrix. Okay, and what else? We have D, and D is A, B, T. So now we have what do we have here? We have a multiplication. Like I said, commutative, commutativity, if this word exists. So here we cannot say that AB transpose is equal to AB transpose. Not true. Especially in matrix, because we need to have, this, even this is different, but this has to be the same to be able to multiply them. So if you have a transpose of a product, you can do a transpose of a product. So you made the multiplication, and then you just calculate the, no, sorry, not the trace, but you just interchange the rows and the columns. Yes, so you invert it, so it is equal to the inverse product of the respective transpose. So you see, you change the place. Yeah, only then it's going to be equal, but the other way is not true. And last, if A is an invertible, this is a new word for you, invertible. I prepared a little bit these videos that I'm doing, so I have an idea of what I'm saying. But if A is an invertible matrix, it means that you can invert it. You will learn how to invert. This is a matrix A. If you want to invert it, it's denoted like this. A transpose is denoted like this, and trace A is denoted like this. So now you know how to, denote the same matrix but transform, transpose, inverse, and so on. So if A is an invertible matrix, then AT, the transpose, is also invertible. is also invertible, and AT inverse is equal to inverse transpose. It doesn't matter if you transpose and then you inverse, or you inverse and then you transpose. You're going to get the same result. Okay, so these are properties. These are properties. Properties. I think that if you are good at if you practice a lot, mathematics is also about practicing a lot. So that's what a teacher told me once. It's okay. This is nice. This is very nice. Yeah, I like it. Okay, guys, so what can we do now? We have heard. Wow, I have another color. So we have heard about square matrix. Square matrix. Now might be the right time to talk about square matrix. I think we're about to end with this video. So better keep it for another time. So we talk about different things in this video. So the last time we finished with elimination, the Gaussian and so on. And then in this one we started with the arithmetic operations. Let me just do a summary. Arithmetic operations. So operations, so what are the arithmetic operations possible? Plus, minus, addition, subtraction, and multiplication. These are possible only if they are of the same size. So this 2 times 2 and 3 times 3. Sorry, this is not possible, yeah. Precisely not possible, yes. Has to be 2 by 2. Same size means this is equal. If it was like this, it should be also like this. It's same size. This is the square matrix, but you got the idea. So we did this. We know how to subtract, to make addition, how to subtract one matrix from another, and we know what is a scalar multiplication, multi. It's when you have a scalar and you have a matrix. So if C is a scalar, it has the value 2, for example, and this is, you just multiply each entry by this and you will have this 2 0 2 0 2 0 0. Okay, this is the scalar multiplication, and then we did two matrices multiplying. We know that there is something to respect. It's that the number of columns in the first and the number of rows should be the same for the two matrices to be able to be multiplied, and the result is always what you have on the edge. So you will have a 2 by 2 matrix. So this is for multiplication of matrices, and then we saw combination of this combination. Yeah, so we saw how to do it, and there is also the linear combination, I think combination, and this is the way that you can multiply matrices to each other. And then wait a second, I am just mixing all my papers, I guess. Sorry, I got where does it start? Yeah, where does it start? That's a good question. So we have this, and then we have this. Which one is which? Yeah, we got it. And then we did something very important. So what is this? Hey guys, what is happening here? Yeah. That's good. Yes, and after that we did the transpose matrix. Sorry. We did also coefficient matrix, transpose matrix, coefficient matrix. We did the trace. Transpose matrix is like this, denoted like this, and then the trace is denoted like this. And then we just touched. We didn't do anything about it, but there's also inverse, and that's it. So that's what we did so far. It's quite a lot, and next time we're going to talk about square matrix, power of matrices, and polynomial expressions. And after that we will do some more other things and so on till till I'm done. Okay, so thank you for watching. Take care and haha. I don't know if I feel like drawing. It seems like he's here now. I wanted to do something else. I want to relax a little bit now. Make this nice drawing and a nice smile. Yes, this guy is nice. Make like that. No, it's not as beautiful. Maybe if I do like this. Yeah, like it. Yeah. And yeah. Okay. This guy is ready to party. So brain damage from staying late. You need to sleep. Bye.